You see, everything in the universe wants to get to a state of lower energy. That's why a ball on a hill will roll down by itself, because that decreases its potential energy. This trend also applies to atoms. The state of lowest potential energy is having a full outer shell of electrons, which is most often 8, or in the case of hydrogen and helium, 2. If you think back to the periodic table, you'll see that all noble gases already have a full outer shell, which is why they don't really want to react with anything. If two atoms don't have a full outer shell, but can achieve one by sharing electrons, they will naturally do so, the same way a ball will go downhill, as their combined energy would be lower than if they were separate. The sharing of electrons is called a covalent bond. These bonds are also caused by the positively charged nucleus of an atom tugging on electrons of another atom. The strength of this pull is called electronegativity. In the periodic table, the electronegativity increases from bottom left to the top right. Therefore, fluorine has the strongest pull. It's just unbelievably desperate for an electron. If the difference in electronegativity is bigger than about 1.7, you get an ionic bond. A good example is sodium chloride. Chlorine would do anything for an electron, while sodium has one too many and just kinda wants to get rid of it anyway. Perfect, they both say, forming an ionic bond, where sodium loses an electron and turns into a cation, and chlorine gains an electron and turns into an anion. That seems pretty important. You might want to remember it. The most common place you see ionic bonds is in salt. Yes, also table salt, but more generally, when metals and nonmetals bond, you get a salt, which is just a grid of ions. Speaking of metals, a pure metal forms metallic bonds. You can imagine this as a huge grid of positively charged nuclei which are surrounded by freely moving electrons. You see, in a metal grid, the valence electrons are kinda promiscuous, or as the nerds call it, delocalized. They can move freely in a giant playground of nuclei instead of being loyal to just one. This kind of bond is responsible for the properties of metals, like conducting electricity and heat, and also being malleable, as in being kind of bendy. Like, you can hammer on this stuff until it's the most deformed, unelegant, and ugly-looking piece of material ever known, and it will just limp along as if nothing ever happened.